All right, for this topic, we want to look at continuity. And for continuity of a function, we're really looking at is the function continuous or not? And that means are there any breaks in the graph or any holes in the graph? And here we want to look at three values at where x is equal to c, which our function f is not continuous. Our first example here, you can see that we have the interval, an open interval from a to b, and our point C inside the interval that we're looking at here. The first graph, you can see that we end up with an open circle here, and that's telling us down here that if we try to evaluate the function at C, f of C is undefined. That means there's no point that satisfies f of C. Okay, there's just simply a hole in the graph, so therefore you would have a discontinuity. In the second graph, again on the open interval from a to b, the point that we're looking at is C. So C is representing some number, and there's an actual split in the graph. If you notice with this example, the function is defined at C because here the function is defined because we have a solid dot, but there's a break in the graph. And if we compare this down here to the limit of the function as we approach the value of C, the limit doesn't exist. And why does the limit not exist? Because if we're approaching C from the left and we're approaching C from the right, notice here we're approaching two different y values. So here you're having two different values that we're approaching, so the limit doesn't exist. If the limit doesn't exist as you approach this value C, then that tells us it's not continuous at that point. The third graph shows us another discontinuity, and if you notice here, the graph is defined at C. In other words, if you plug C into the function, f of C, we do end up with a y value at C, and it's defined here at whatever this y value is. But if we look at the limit, we will also notice that the limit also exists. If we approach C, this value C from the left and from the right, the limit exists as well. But the limit of the function as x approaches C does not equal the function evaluated at C. And that's because this open circle, basically, we redefined this point and moved it up here, causing the hole in the graph, which causes the discontinuity. So here we have three different situations indicating a discontinuity at a point. The first one is the function is undefined at C, or the limit does not exist as x approaches some point C, or if your limit of f of x does not equal the function evaluated at the point. So if we look at defining the definition of a continuity at a particular point, a function is continuous at C if the following three conditions are met. And this is referring to the following three examples that we just looked at here. The first case is f of C is defined. So obviously your function has to be defined at the point. Number two says the limit of the function as x approaches C has to exist, because if your limit doesn't exist, that means you're approaching two different values, which means there must be a split in the graph or it's going to infinity. And the third example is the limit of the function as x approaches C has to be equal to the function evaluated at C. So if all three of these conditions are met, then your function is continuous at that point. And if the function is continuous at all the points on the graph, then therefore your function would be continuous everywhere. So let's look at an example of this one here. If we go through all three of these conditions, the first condition up here, f of c is defined. So if we go through that, if we're given this function here, f of x equals x minus 3 squared, and we're going to just pick a point, and over here I've picked the point here. This is our c value. We're going to say 4. We can pick any point we want, but I'm going to use 4. So if we look at f of c, so that's f of 4, well, what happens? Well, if we plug 4 in, you get 4 minus 1, 4 minus 3 is 1, 1 squared is 1. So f of 4 equals 1. So that indicates that our function is defined at that particular point. Okay, so therefore that one checks out. Number 2, it says the limit as we approach that c value exists. Well, if we look at the limit of our function as x approaches, and our c value, again, I'm just using the number 4. Well, as we approach 4 from the left and the right, hopefully you can tell here if we're approaching 4 from the left side and the right side, we're approaching 1. So once again, our limit exists, so therefore that condition is met. And the third condition is the limit of our function as x approaches our c value 4 has to be equal to the function evaluated at 4. Well, this is actually saying that condition 1 and 2 are going to be equal, because from condition 2, the limit of our function as x approaches 4, we already know that is 1. And the function evaluated at 4 from condition 1 up here, that's equal to 1. So therefore, condition 3 is met. So that tells us that our graph is continuous at that point. Now we know this is a nice polynomial function. We end up with x minus 3 squared. It's a nice quadratic function. And we already know that it's going to be continuous everywhere because the quadratic has no breaks or holes in the graph. And you could pick any point on this graph and it would meet all 3 of these conditions. And what that tells you is that this graph, the function, is continuous everywhere. Okay? Now, our discontinuities, there's 2 different types. One type is a removable discontinuity and a second is non-removable. If we look at the first type, the first example here, we have a graph. Our function is f of x equals x squared minus 1 over x minus 1. And we know that because we have division by 0, when x is 1, the denominator is going to 0. So clearly at 1, we have this hole in the graph. And we can see that we're going to have a discontinuity. So the question is it removable? Well, if we look at x squared minus 1 and we take and we factor x squared minus 1 is a difference of squares, x plus 1, x minus 1, what happens? The x minus 1 factors cancel, and we're simply left with x plus 1. What happened to the discontinuity? It disappeared. So here we've actually removed the discontinuity by canceling out the factor, and essentially now if we were to look at the graph of x plus 1, we've essentially filled in that hole in the graph. So here we have a discontinuity at x equals 1, and it is considered to be removable. And you're going to notice that when you look at the graph, if there's just a simple hole in the graph here, and here we just have a straight line and there's just a hole there and then the graph continues. Typically, if you just have a hole in the graph, your function's discontinuity is going to be removable. Now, if we look at the example over here on the right, here we can look at the graph and we notice that there's actually a split in the graph. And I'm going to go ahead and tell you that when there's a split like this in the graph, obviously there's a discontinuity and it's going to be non-removable. For example, the function here is going to be made up of a piecewise function where f of x is equal to 1 when x is less than or equal to 2, and that gives us the straight horizontal line, and f of x is equal to x for values of x that's greater than 2, and that gives us the other part of the graph going up to the right. And if you notice here, the conditions that we're looking at, there's no way to remove this discontinuity. For example, if we went through the conditions that we had above, the first condition says if f, the discontinuity here is at 2, so f of 2, well, that's defined because the function, if we plug 2 into the function, 2 is less than or equal to 2, so that would be this first part. So we know that the function is defined to be 1. But if we look at the second condition, where we're trying to look at the limit of the function as x approaches 2, well, if we approach from the left, our limit is approaching 1. If we approach it from the right, our limit is approaching 2. So therefore, the limit does not exist. So this condition is not met, which tells us we do have a discontinuity. And for this example, it's non-removable because there's no way for us to redefine because there's an actual split in the graph. There's no way that we can connect these 2 points here together. So therefore, it's a non-removable discontinuity. Okay, so with having the non-removable discontinuity x equals 2, in this example and the example on the left, we simply had a discontinuity at x equals 1, which is removable. So there's your 2 different types of discontinuities when working with your functions.